We're working in section 5.1. We're learning to solve systems of linear equations. In the first video, we learned the substitution and the elimination method. And now we want to talk about how many solutions a system of two linear equations can have. And so I would just remind you of example 2 from the previous video, where we had a 2 by 2 system and we had exactly one solution. We had the ordered pair 3, 2. Could you have more than one solution? Could you have less than one solution? How many solutions can you have if you start with a system of two linear equations? So let's think about this problem graphically. The graph for each equation in the system is a line. And so the solution of the system is where the lines intersect. How many different ways can two lines intersect? So first, we should think of the most common way. I've drawn two lines. I'm going to label them L1 and L2, although that's not so important. And you see they intersect at exactly one point. And so there is exactly one solution. And this was the case in example 2 and also in the first example that we saw in the previous video. When there's exactly one solution, we say that the system is consistent. And we say that the equations are independent. Okay, what else could happen? Well, if you think about it, what if the two lines were parallel? How many solutions are there then? Then there's no solution. The lines are parallel. In this case, we say the system is inconsistent. The system is inconsistent. Still, the equations are independent. Okay, we haven't seen an example of that yet, but we have one coming. There's one more possibility. It's a little trickier. What if the one line and the other line were exactly the same? That is, the second line lies right on top of the first line. Then there are infinitely many solutions. Then every point on the line is a solution. And so there are infinitely many solutions. We say the lines are coincident Lines are coincident, like as in they coincide with each other. And then in this case, the system is consistent but the equations are dependent. Okay, so a system is consistent if there is at least one solution. A system is consistent if there is at least one solution. So that would be the first case or the third case. And then the equations are independent if there are a finite number of solutions. So that would be the first case and the second case. Independent equations. Okay, so let's go ahead and see some examples of parallel lines and coincident lines. So let's go to example 3, solve the system. You could do this by the substitution or the elimination method. For me, I think the elimination method seems a little easier, but it really doesn't matter. We'll get to the same result either way. So if we want to use the elimination method, we could multiply the first equation by 2, and that would give us 6x minus 4y is equal to 8. And the second equation just comes down. And then the interesting thing is that when you add the two equations together, I was thinking of canceling the x's. I multiplied by 2 so that 6x minus 6x would cancel. But it turns out that the y's also cancel. Minus 4y plus 4y cancels. And so what are we left with on the left side? We're left with 0. And on the right side, we have 8 plus 7 is 15. This is not true. We learned a long time ago at the beginning of the semester to call this a contradiction. And so we conclude that there is no solution. And we can write out the words no solution. We could also write this symbol for no solution. And we could also write out this symbol for no solution. And we've seen those earlier in the course, and so it's nice to be reminded of them again. And furthermore, it's worth making a couple of observations. We should remember that the lines are parallel and that the system is inconsistent. Okay, so that's example 3. Let's go on and let's look at example 4. We have another system to solve. Again, substitution or elimination would be fine. I will choose elimination. I will multiply the second equation by 2. When I do that, I get negative 8x plus 2y is equal to 4. And then I can just bring down the first equation. And this time, when I add the two equations together, x's and y's both cancel out, just like in the previous example. But on the other side, 4 minus 4, those also cancel, and so we're left with 0 equals 0. We learned a long time ago to call that an identity. And the conclusion then is that there are infinitely many solutions. We could also go on to say that the lines are coincident and that the equations are dependent. But the most important thing is, how are we going to write the solutions? We don't just want to stop and say there are infinitely many solutions. We want to go on and describe what they are. Can x and y be anything? No, they can't. The ordered pair x comma y, that's the solution, is not just anywhere. Those ordered pairs are points on the line. And again, when we see this infinitely many solutions, we know that these two lines that we started with are equivalent. They're actually the same line. That's what it means for them to be coincident. So we need to describe the points on that line, and the directions in the homework might say something like, set y arbitrary. And so what does that mean? That means that we're going to let y be any real number, and then the value of x depends on what we choose for y. So what we need to do is we need to solve one of the original equations. We need to solve one of the equations for x in terms of y. When we solve for x, then that must be in terms of y, because y is the other variable. So when we set y arbitrary, we solve for x. So let's take that first equation. It doesn't matter which equation we use, they're equivalent. Let's take that first equation and let's solve for x. And so we'll have we'll add 2y to both sides, and we'll have 8x equals 2y minus 4, and then we can divide by 8 on both sides, and we have x is equal to, let's see here, maybe we could just take a common factor of 2 out of each term in the numerator, and then cancel it with a factor of 2 in the denominator. And so that would get us y minus 2 over 4. And so then the solutions are ordered pairs. And the way we're going to write them is we're going to write, instead of xy, well, y is fine because y is arbitrary, but then x is the same as y minus 2 over 4. And so this is the form of the solutions. Actually, I want to put curly braces as well to say that this is the set of all ordered pairs where y is any real number, and then x has this particular form. X is y minus 2 over 4. So there's the solution that we're looking for. it's a little bit weird to write an ordered pair that way. So let's make sure we understand what some actual solutions are. Could you give an actual point on the line? What are some particular solutions? So again, y can be any number, so pick a number. If we let y equal to 0, then we plug that into the expression for x. We get 0 minus 2 over 4. Minus 2 over 4 is negative 1/2. So negative 1/2 is x. Remember, we said y was 0 in the first place. We could do this for any number. We could let y equal to 1, and then for x we would have 1 minus 2 is negative 1/4, comma 1. Or if you wanted to make the numbers come out a little nicer, you could pick y equal to 6, and then 6 minus 2 is 4 over 4, which is 1. So x is 1 when y is 6. And so those are just a few examples of points on this line that we're trying to describe. Okay, we'll stop there. I have another example here, which I'll show you in the next video.